Dear colleagues, today, in the context of the COVID-19 pandemic and global self-isolation, many companies suffer losses, and people use virtual tools for work and communication. Many services cannot cope with the many times increased activity, which is largely due to the problems of existing data centers. Now it's obvious that the data center industry will continue to actively develop, but in the conditions of global crisis, more reliable solutions with low CAPEX and OPEX will be in demand. In our webinar, we will tell you how to create the conditions for sustainable development of data center industry as a whole. And for participants will be provided tools and opportunities to achieve them. For more than a century, we have been providing solutions to maintain the necessary conditions in various fields, from cooling diesel engines to greenhouses for growing cannabis. And as expert, we receive requests for reliable, high quality and simple solution for cooling the data center. As a result, those who have turned to us got a solution that fully satisfied their needs. We know about the problem of overheating zones, the high cost of building a data center, the requirement for high degree and reliability and redundancy, and the desire of each owner of a commercial data center to minimize operating costs. But there are always two scenarios. In the classic version of data center cooling, with crack and in-row coolers in most cases, the real power does not reach the calculated capacity. And server racks with powerful servers are half full or less. The owner of the data center is losing money due to an inefficient engineering infrastructure. The required full electrical power of data center is 1.5–3 times higher than the IT load. The high cost of construction does not allow to implement or turn into unfinished construction about 60% of data center construction projects. The operation service of each data center is involved in an endless process of balancing airflows. All thermal energy is utilized in the environment. An alternative to the most efficient cooling of data center with the electric submersible servers requires new construction. Here is the calculation of the crack unit, which is designed for air 3816 and a total cooling capacity of 65 kW. It is stated that the sensible capacity is 51 kW with an airflow of 7000 m3 per hour with air delta T of 22 Kelvin. In reality, air delta T is determined not by crack units but by the servers. And in this case, the crack unit will cope only up to 55% of the load. Exceeding this load, the energy consumption of compressors will be increased, but without obvious success. I want to note that this is an example for water unit, and for direct expansion system the situation is more deplorable, because evaporating temperature, for example for 410 Freon, is 15 degrees, and the sensible capacity is even less. By limiting the airflow through the raised tile in the front of the rack, when placing powerful servers, the rack is filled 30%. For example, by limiting the power per rack to 10 kW and the use of servers of 1 kW, we can fill only 10 of the 42 units. According to the Uptime Institute, the PUE of the largest data centers has dropped to 158 in 5 years from 2013 and roll it back over the next 1 year and even exceed this value. Here we see the impact of inefficient cooling system in excess of the value of 50–60% of usable data center load. and such data centers begin to lose money every day. From open sources, on the example of calculating the distribution of the total energy supply to the corporate data center in peak mode, we see that the share of IT load is only 30%. In commercial data centers, this figure is closer to 60%. I note that this is a very significant indicator for evaluating investments. Data center construction cost of 1 megawatt range from $15 to $30 million, depending on the level of security that has a serious impact. Thus, 75% occur in the material and 25% for installation work. In my calculations, I took the average cost $22.5 million per megawatt. As you can see, there are many components in the materials, but I would like to draw attention to how high the share of power equipment is 64%, what I mentioned in the previous slide. For 1 megawatt cooling, we need air delta T 12 kelvins and airflow 70 meter cubic per second. When passing through a narrow section conditioner with high resistance to heat exchanger, we obtain a considerable pressure drop, which leads to the appearance of a Venturi effect, causing overheating zones. Due to the need for high overpressure, we see a pressure drop along the air circulation loop of 200-400 Pascal, which also leads to a high energy consumption by fans and their shorter life. For air-air systems, this figure is higher due to longer distances. The temperature of the liquid at the outlet of the close control air conditioners is about 15-20 degrees and does not allow heat recovery without the use of heat pumps. In turn, investments in heat pumps are not profitable at current prices for heat supply. To discharge heat into the environment without using mechanical cooling, the free cooling modes use the sea, lakes, underground aquifers, and in most cases ambient air. Thus, we not only throw money down the drain, but also damages the environment. The most effective server cooling solution on the market is the electric immersion server cooling, but it has a significant limitation for large-scale use. The cost of the cooling system is $30 million per megawatt. Other restrictions I would include requirements for the area of equipment placement, single level, drainage and the electric on the floor, the restrictions on the use of hard drives and optical connections. Now we will consider another option where we can achieve the required cooling power in the entire load range, use racks with a load of up to 19 kW, conditionally reduce operating costs to 100%, achieve IT load conditionally 100% of the full data center capacity, reduce CAPEX by $4 million per megawatt, to build a data center without problems in future operation, with additional source of income, and get an affordable alternative to immersion cooling. Industrial low-speed ventilation air coolers are designed according to the needs of the servers, and due to the large cross-section and large heat exchange area, they provide clear cooling capacity over the entire load range without condensate and extremely low power consumption of fans. You see the CFD modeling which was carried out by our customer for a hall with 48 racks with an average power of 28 kW, which proves the ability of low-speed ventilation to work with high-density racks. There is also a solution with loop heat pipe that allows you to remove up to 500 watts from one processor. When placed in a single rack, 40 servers with 4 processors in each server may be removed from one rack 80 kilowatt using loop heat pipe and another 10 kilowatt using air cooling. I will talk more about this solution later. In this graph, we expressed the data center energy consumption in physical terms with 4 solutions. The first based on closed control units, the second based on low-speed ventilation, the third based on low-speed ventilation without chillers, and the fourth based on loop heat pipe Tercon. It shows that the difference between the first and third solution is about 1,500 megawatt hours per year, which at cost of 13 cents per kilowatt hour is equal to $200,000. This saves about $2 million per 10 years. And in this case of loop heat pipe Tercon, thanks to a 10% reduction in IT load due to passive heat dissipation without fans, these savings turned out to be twice as much, and the conditional annual power consumption of the data center turned out to be less than the IT load. It means conditionally OPEX reduced by 100%. On this slide you can also see an increase in the reliability of the system. If you look at the energy consumption of cooling systems, in the second case it is half as much thanks to the low-speed ventilation and a higher temperature for free cooling. The chiller works 3 times less and its service life is longer. And in the third and fourth case, chillers are simply absent. Thereby, we get a more reliable solution with an interesting bonus on next slide. As you can see, the extremely low power consumption of low-speed ventilation fans and the use of innovative adiabatic coolers can increase the useful share of IT load up to 85% of the full data center capacity. And in the case of LHP Tercon, it is possible to make the total data center power less than the calculated IT load. So as the capacity of the auxiliary equipment is less than 10% reduction in the IT load due to passive heat removal of heat from processors without fans. All this has an impact on energy and on the UPS and directly on the cooling system. And on the next slide we will see how this will be reflected in investments in the data center. We see a not obvious trend. The more efficient the system, the lower its total cost. And the main savings are in the energy sector, secondly in the UPS, and then the third turn in the cooling system. Therefore, I want to draw attention to the fact that it is important to look at the total cost of construction and not the individual cost of the components. The low-speed ventilation design provides for the operation of the server room and the coolers as a whole. Therefore, there are no bottlenecks, weaknesses. The large cross-section of the coolers gives a low and uniform air flow rate along the entire path with a resistance of less than 30 Pascal, which create conditions for the absence of pressure drops that could lead to appearance of the Venturi effect and overheating zones. On the other hand, it is opportunity to work without overpressure, to drastically reduce the power of fans and their heat dissipation. In all existing low-speed ventilation data centers, service staff are not aware of problems with overheating zones. The temperature of the liquid at the outlet of low-speed ventilation is possible up to plus 32 degrees, and at the LHP Tercon up to 55 degrees, without the use of heat pumps. This means that such data centers are immediately ready to integrate into the social infrastructure and provide the possibility of preheating the tap water and heat supply of buildings equipped with a system of underflow heating. A water of 26 degrees is enough to ensure a comfortable climate in the room. The potential for using that solution, for example in Germany, is 10% of the country's entire electric energy system. At the same time, we reduce the significantly negative effect on the environment. We reduce the CO2 emissions of classic heat supply sources. We obtain a stable source of income from sales of heat energy and create conditions for the sustainable development of the data center industry. With an innovative solution for servers cooling from Tercon LHP, we reduce the energy consumption of the IT load by reducing the fans due to passive heat sink with a dry lock to the cooling rail at the end of the server rack. It is possible to use 85% of existing servers, among which IBM, Dell, Lenovo and Supermicro already use this technology. Integration in water-cooled data centers as well as micro data center design. We advise you second option, since in the case of low-speed ventilation solution, you will receive a combined savings of OPEX and OPEX $6 million per 10 years. And with Tercon, you will receive a total savings of $9 million per 10 years and additional income from heat supply. And then compared with the immersion option, only $17 million in capex. And all this without any problem in operation. All participants in the data center industry benefit from a good and high quality solutions. One of our clients has already implemented 2 data center projects in Kazakhstan, one with crack units on the water and the second with in-row coolers also on the water. And he wanted to build next one both more efficiently and cheaper and choose the LSV solution without a chiller with adiabatic coolers. Another of requirements was a lack of raised floor due to low ceilings and a server room without access by service personnel. All engineering infrastructure beyond. Each low-speed ventilation cooler has a rated capacity of 40 kilowatts with an energy consumption of 500 watts. And in general, the system has an average annual PUE of 1.075 and a maximum design temperature of plus 43 degrees. Innovative adiabatic cooler allow you to work 85% of the time in a year in a dry mode, and the rest of the time use a minimal amount of water without water treatment. The test at maximum load showed the consumption of adiabatic coolers at an ambient temperature of plus 5 degrees only 30 watts due to a large heat transfer area. Today, many data centers at plus 5 begin to turn on the chiller for cooling. Our other client, a commercial data center in Moscow, already used air-air systems, direct expansion systems, water-based systems, and was looking for the most effective solution for server cooling. And he decided to apply a solution on loop heat pipes Tercon technology with a passive heat removal from servers processors and installed one rack for testing. In rear part of rack can be seen the bus to which are attached a dry lock of loop heat pipe. And the fluid circulates in the bus, which removes heat. Moreover, this bus has two inputs and outputs, which provides redundancy. At the top you see the energy consumption of classic servers, and below the energy consumption of the servers equipped with LHP Tercon. Real-world testing showed a 15% reduction in load. DataPro also tested the low-speed ventilation system with adiabatic coolers without chillers. In the summer, many colleagues from the data center industry were invited to test in order to personally verify the effectiveness of the system. The power consumption of 125 kW low-speed ventilation unit is 1 kW with an estimated PUE of 1.07. And the next client in the Netherlands already had a commercial data center with crack units in Rotterdam and was building the next one in Groningen. And he chose the low-speed ventilation solution with lower PUE, cheaper general capex, and no raised floor. Part of low-speed ventilation is visible in the background. Low-speed ventilation fans rotate at low speed and minimal power consumption. The system is based on dry coolers for free cooling and series connected air-cooled chiller with a calculated PUE of 1.10. A high switching point for free cooling allows 75% of the time in a year to work without a chiller. The cooling of the room with UPS also occurs using low-speed ventilation, which are suspended from the ceiling and significantly reduce the used area. Our solutions are available to each of you, and if you choose the second option, then we will help you to create a cooling system that meets your needs. For you who spent your time listening to the webinar, we are ready to offer the following services for free. Integrated calculation of the engineering infrastructure of data center, which include 3D drawing of your data center, equipment selection proposal with details, PUE for your climate zone, and calculation of total data center ownership for 10 years, and commercial offer which include all these components. Thank you for your attention, and next part will be taken for answers and questions.